Okay, so let's start. What I would like to discuss today is some introduction to primes in arithmetic progressions. So, in the abstract of the course, there was also some things about Gauss circle problem and Dirichlet divisor problem, but as to not overload this course with some technical stuff, I will maybe include these topics into the problem sets. Okay, so today I would like to start the discussion on primes in arithmetic progressions. Let me remind you the statement of the Dirichlet theorem. This will probably be proved today. Suppose that Q is a positive integer, A and Q are prime, then there are infinitely many primes P which are congruent to A modulo Q. You can add here that moreover sum over all P congruent to A modulo Q, 1 over P diverges. So there are lots and lots of primes congruent to a given number modulo Q, so that this sum is actually divergent. Okay. Расходится. Aha. So let me give a brief introduction here. So equivalent statement of this theorem is that for a polynomial P of n equals what? Equals Qn plus A. There are infinitely many primes of the form P of m, right? So what is widely believed is that, let me state it as a hypothesis, that if P of n is a polynomial with integer coefficients, then under some natural restrictions, there are infinitely many primes of the form P of m. So what are the natural restrictions here is that first, maybe zero, the leading coefficient of P of n is positive. Otherwise, this, of course, is trivially untrue, right? And the second condition, what is the second condition here? When we have, we obviously have only finitely many prime values.
Коэффициенты не взаимопростные.
One can generalize this condition on non-comprimality. P of n should be irreducible in z of n, right? So, for example, there are, of course, only finitely many prime numbers of the form n squared plus n, correct? If n squared plus n is prime, then n is equal to 1. Okay, and there is also one more condition which will suffice, is that you see, if you take n squared plus n, it is not a prime because it is n multiplied by n plus 1. But there is another reason, right? N squared plus n is always even. So, for example, n squared plus n plus 2 is an irreducible polynomial with a positive leading term, but all its values are composite. So the second condition will be that the congruence, say non-congruence, the non-congruence P of n is not congruent to 0 modulo P is solvable for all P. Obviously, this condition can be checked for finitely many prime numbers. So, for example, we do not conjecture that this polynomial has infinitely many prime values, but for a polynomial of the form, say, n squared plus 1, we do conjecture this. Okay? This hypothesis is known to hold only. Yeah, maybe I missed something, but I don't really.
What's the last condition? Sorry.
The non-congruence P of n is not congruent to 0 modulo P is solvable for all P.
А для целозначных магазинов это верно?
И для целозначных, я думаю, предполагается, что верно. A general ideology here is that if you have some sort of algebraic statement about prime numbers, then usually it is either, say, existential algebraic statement about existence of infinitely many or something like this, then this statement is usually either trivially false or true. And this hypothesis is only known for the polynomials of this form. So for polynomials of degree greater than 1, it is not known at all for any cases. So there are no examples when we know anything like this. And you will see that the proof of Dirichlet's theorem is very, very specific for the linear polynomial, so there are no obvious ways to generalize this. Okay, so to prove this, we first need lots and lots of new definitions. Namely, we are going to deal with Dirichlet characters and Dirichlet L functions. Dirichlet characters. So what is Dirichlet character? Chi from natural numbers to C is Dirichlet character if chi of n is equal to 1, chi is completely multiplicative. Of course, this condition is redundant because we defined completely multiplicative functions as functions which are not identically 0, but still, chi is completely multiplicative, and also chi is periodic. There is a Q natural number such that chi of n plus q is equal to chi of n for all n. So basically, you define your character on residues modulo q and then continue it by periodicity, right? So if you have say if you have some function psi from z over qz to c, such that psi of ab is equal to psi of a, psi of b, and psi of 1 is equal to 1, then you can continue this function to the function on the set of all integers, right? This is an obvious projection. Okay, so this is a definition of Dirichlet character, and let us also notice some things. First of all, for
Утверждается ли, что любой характер Дирихле имеет такой вид? Пропускается через...
we will discuss it, okay? So first of all, if A and Q are coprime, Q is a period of chi. Of course, any chi has infinitely many periods, right? And the set of all periods form a homogeneous arithmetic progressions.
Мы сейчас что конкретно обсуждаем? То есть свойства?
Yeah, assume that you have a Dirichlet character which is periodic with period Q. Then we can notice the following things. So, first of all, if A and Q are coprime, then chi of A has absolute value 1. How to prove this statement? Well, A to the power phi of Q is congruent to 1 modulo Q, right? So chi of A to the power phi of Q is equal to 1. So actually all the values of A at invertible residues modulo Q are roots of unity. Correct? Now,
A to the power of phi.
A to the power of phi of Q. Phi is Euler-Totian function. This is Euler's theorem. You probably know the proof. Okay, so this is just a statement that the multiplicative group of Z over QZ has a finite exponent. Dividing phi of Q. Okay, the second is, well, why do we consider all the periods? Let's consider only minimal period. If Q is the minimal period of chi, and say B and Q are not coprime, then chi of B is equal to 0. How to prove such a statement? Well, you can always you can always do the following. B will be equal to some say D multiplied by F, and D is divisor of some power of Q, so it consists of the same primes as Q, right? And F and Q are coprime. Then what can you do here? Well, phi of F, as we know, has absolute value 1. It is a root of unity. So we get that if chi of B is not equal to 0, then chi of D is not equal to 0, right?
And you can also take, say, D1 to be the greatest common divisor of, or you can take something like you can take something like D modular. No, it's not the best idea. Sorry. You can take you take the greatest common divisor of D and Q. Then, of course, D is equal to D1, D2. So chi of D1 is also not equal to 0. So basically, if you have some integer which is not coprime to our minimal period, such that the value of character is non-zero, then you can you can find a divisor of Q such that the value of character on this divisor is also not equal to 0. Right? Obviously. Okay, so
Еще раз можно?
you can forget about this stuff and just say that D1 is a greatest common divisor of B and Q. And then you conclude that if chi of B is not equal to 0, then chi of D1 is also not equal to 0.
Дальше продолжаем.
So now what we can do, we can obtain a contradiction. So you see, chi of n plus q is equal to chi of n, right? For instance, chi of d1n plus q is equal to chi of d1n. And this is equal to chi of d1 multiplied by n plus q over d1. Right? Then this is equal to chi of d1 multiplied by chi of n plus q over d1. So you get that q over d1 is a period of chi. Correct? Nice. This means that d1 should be equal to 1. And we assumed that b and q are not coprime. This is a contradiction. So basically, what is happening here is that you have your minimal period q, and all the invertible residues modulo q go to some roots of unity multiplicatively, and all the non-invertible residues go to 0. So let me give another definition. Chi is Dirichlet character modular q if q is a period and chi of n is equal to 0 for all n such that n and q are not coprime. Okay, so let me write the commutative diagram once again. What is the meaning of this definition? You can consider the following semigroup. You can take z over qz star, so invertible residues, and then you can add 0, which will act as 0 on everything, right? Then you can organize a projection here from Z to this semigroup. The projection works as follows. All the invertible residues go into invertible residues, and everything non-invertible goes to 0. And now you have some character in the group sense of this thing. So you have some psi union 0. So 0 goes to 0, and restriction on the invertible part is just some character. then you have a homomorphism here, so with 0 once again. And then you have this commutative diagram, and you have your character chi. Is this clear?
Можно все-таки пояснение? Еще раз, наверху что мы сделали? Просто пси с нулем или что?
Мы взяли, значит, взяли остатки по модулю Q, которые обратимы, добавили к ним искусственно 0. Из Z в это можно отобразиться.
Да.
Как? Можно взять у обратимых остатков остаток по модулю Q, а необратимые все отправить в 0. Дальше мы берем какой-то гомоморфизм. Вот отсюда, вот сюда, то есть характер, как группы, одномерное представление.
Ой, фу.
Вот, да ладно вам. Так вот, дальше А0 отправим в 0. И вот если ваш характер хи замыкает эту коммутативную диаграмму, то тогда хи является характером по модулю Q.
Зачем мы предполагаем, что хи-1 равно мы уже доказали?
Это мы доказали только для минимального периода. This is a different definition.
So remark will be that if...
Сверху что получается? Пси с чем объединить?
С нулем. 0 в 0.
If what? If chi is a character modular Q, then it does not follow that Q is a minimal period. It follows in the other direction. If you have a minimal period, then your chi is a character modulo this Q. But in this direction, you don't have an implication. Let me give a simple example. There is a character chi4 of n, which is one of my favorite non-trivial Dirichlet characters. Chi4 of n is equal to the following. It is equal to +1 if n is congruent to 1 modulo 4, -1 if n is congruent to -1 modulo 4, and 0 if n is even. Okay? This is obviously a Dirichlet character. It is periodic with period 4, and it is multiplicative because of the definition, right? Okay, so I claim that chi4 is a character modular, say, 8, right? Because, well, 8 is, of course, a period, and if some n is not coprime to 8, then it is even, and value of your character is equal to 0. And minimal period of this character is, of course, equal to 4. For certain reason, we will need to consider the set of all characters modular a given Q. Okay, so why do we care about Dirichlet characters? What is the use of them? So let me formulate this as a theorem. This theorem will be like almost completely obvious. Orthogonality of characters. So the first statement is that if chi is a character modular Q, and let me give another definition here. It is a very simple one. Definition chi0 Q is the principal character modulo Q if chi 0 Q of n is equal to 1 if n and q are coprime and 0 otherwise. Okay? So for any q you have the following very easy character modulo Q.
Русский главный.
По-русски главный, да. Главный характер. Okay, so assume that you have chi character modulo Q non-principal. And what else? Then we have the following formula. Sum over all A modulo Q chi of A is equal to what? Can you guess? For this character, modulo 4, what is the value of the sum?
Если там по всему, то 0. Или...
0, of course it is equal to 0. Yeah, of course, for principal chi, we get phi of q, right? For principal characters, you just get all the coprime residues are 1 and all the non-coprime residues.
Еще раз, хи 0,q получается.
Sometimes it is also denoted just chi 0 because sometimes you only restrict yourself into looking at characters modulo a fixed modulus, and then there is no confusion modulo which q you consider the principal character. But actually this of course depends on q. Okay. So there is a statement 1 that this sum is equal to 0, and the second statement is that sum over all characters chi modulo q of chi of A is equal to what? Is equal to phi of q if A is congruent to 1 modulo q, and 0 if A is not congruent to 1 modulo q. Okay? So this simple orthogonality allows one to kind of detect congruences. Okay, so let us prove this theorem. The proof will be more or less straightforward. So the first one, chi is non-principal. So there is a B modulo Q such that B and Q are coprime.
Извините, еще раз формулировку можно?
What?
По поводу формулировки еще раз. Вот у нас получается для главных идеалов будет...
Главных характеров.
Характер.
Для главного характера будет fiat Q, а для неглавных будет 0.
The right expression doesn't depend on principality.
There is no principality with the sum of all characters.
Over all characters. Supposed to put principal and principal.
Yeah. Okay, so let us prove the theorem. So if chi is non-principal, then there is a coprime residue modulo Q, invertible residue, such that chi of B is not equal to 1, right? By definition of non-principality. Okay, so multiplication by B is a bijection on residues modulo Q, right? This is because it is, for example, injective, right? Because B is invertible. Okay, so it is a bijection. So the sum over all A modulo Q chi of AB is equal to the sum over all A modulo Q chi of A, right? Because multiplication by B is just a permutation of residues. And this first sum is equal to chi of B multiplied by the sum over A mod Q chi of A. Correct? And so we get the desired result. Sum chi of A is equal to 0.
Nice. We got it. So this statement is basically a very special example of basic representation theory, right? If you take your finite group to be Z over QZ star, then this is just a representation theory for this group. Okay, so let us prove the second statement. The second statement was that we can evaluate sum over all chi modulo Q chi of A, where A is fixed, right? So what I would like to prove is that for any A not congruent to 1 modulo Q, there is a character chi such that chi of A is not equal to 1. Right? So to do so, what can we do? Yeah, something like this. So
Рассмотрим порядок К вот в этой мультипликативной группе. Возьмем значение такой корень из единицы.
And then what?
Образующим.
So look, you have this group Z over QZ star, and you have a subgroup generated by A, right? Suppose that order of this subgroup is equal to K, which is the same as the multiplicative order of A modulo Q is equal to K. So A to the K is equal to 1, and A to any smaller power is not congruent to 1. Then this Z over QZ star can be represented as
По-моему, надо так. У этой вот звезды есть образующая, и мы назначаем им корень из единицы, которая в степени.
It does not have a generator, right?
Ну, несколько, там можно выбрать там. Ну, это
Есть несколько образующих, это тоже можно, да.
Вот мы знаем, что переходит А, и мы просто назначаем образы этих образующих так, чтобы они в степени, в которой они дают А, переходили в корень из единицы, которая в той же степени дает тот корень, в который перешло А.
Okay, so you can forget about this. So this is equal to the product of all p to the alpha exactly dividing q, z over p to the alpha z star, right? And you can consider projections of A on these subgroups. So for some alpha, there is for some p and some alpha, we have the following:
A is not congruent to 1 modulo p to the alpha. And if you construct such a character modulo p to the alpha, then you can continue it on the whole group, right? Correct? So assume we proved it for any prime power. Then we can prove it for everything else, because you have natural projections from here to here, right? So you just use projection and then apply your character. Okay, so what do we do for prime powers? Well, for prime powers, you have what? You have you have that this group is cyclic, right? At least when p is not equal to 2. Correct? So you can choose a generator G and set chi of G is equal to exponent of, say, 2 pi I divided by p to the alpha minus 1, p minus 1. Okay, so then you get this thing. So maybe some easier proof of this result will be part of the exercises next time. So this sum then is equal to what? It is equal to, so there is a chi1, let's denote it by chi1. It is equal to the sum of all chi modulo q, chi of a, chi1 of a, right? So multiplication by a character also only permutes your characters. So it is equal to chi1 of a multiplied by the sum of all chi modulo q, chi of a, and then you get the desired result, right? Any questions about this?
Почему, когда, вот если мы во всех множителях, которые z по степени альфа z, получили образы проекций не единичные, почему их произведение будет не единичным?
Не, меня это не интересует. Я беру, у меня есть какой-нибудь образ, который не единичный.
В смысле?
Я по нему делаю, а по остальным просто единицу.
Okay, so what we proved is known as orthogonality of characters.
There's also, what if A is equal to 1 modulo Q?
Okay, if A is equal to 1 modulo Q, then you have the sum of ones over all characters,
Yes.
and the statement of theorem is there are exactly phi of Q characters modulo Q. This statement is equivalent to the fact that the dual group of any abelian group is isomorphic to the group itself. Okay?
So the number of homomorphisms from...
Yeah, the number of homomorphisms from a finite abelian group to the complex numbers is equal to the size of the group. Okay, so this will be an exercise.
Let us continue with analytic stuff, okay? So what is the use of this theorem? Well, first of all, we can define, finally, let us define Dirichlet L function. Dirichlet L function is defined as follows. L as chi is equal to the sum of all n from 1 to plus infinity, chi of n divided by n to the s. Okay? Now, by definition of Dirichlet character, this is also equal to the product of all primes, 1 minus chi of p divided by p to the s to the power minus 1. This is because every Dirichlet character is also completely multiplicative. Right? So what can we do next? First of all, let us prove that this is a nice function. Corollary. If chi is non-principal, then
Is minus 1 in the power
in the power of what? So you have this parenthesis, and you get minus 1, this parenthesis to the power minus 1, as usual. If you have any completely multiplicative function, you have this formula, right? Okay, so if chi is non-principal, then this function is holomorphic for sigma greater than 0. Okay? So it is obviously holomorphic when sigma is greater than 1, because you can do the same thing as for the Riemann zeta function. You can just prove an absolute convergence. And if sigma is greater than 0, you can do something else. Proof is rather obvious, so define the following. S chi of t will be the sum over all n less than or equal to t, chi of n. Then what can we say about S chi? I claim that absolute value of S chi of t is less than q, always. Is this obvious? What? Correct. So you have any interval from 0 to t, and then you
n less or equal to
n is less than or equal to t. Sum over all small n. So if you have your interval of summation, you can cut it into parts of length precisely q, and then you end somewhere here for some k, and then you have an interval of length less than q, right? And sum over every period is equal to 0. So this is less than q. This is completely obvious. This is true for any function which is of absolute value at most 1 and with average equal to 0.
Okay, but for every period it's 0, but there's some length.
Once again, here you have 0, here you have 0, here you have 0.
And then why is the rest is less than q?
So you have the largest k such that qk is less than t, and then the remaining part has length less than q, right?
And it can be bigger than 1.
Can be what?
Well, why the sum would be less than q?
This is because every value of the Dirichlet character is either root of unity or 0.
Okay.
So you have certain summands, and some of them are equal to 0, some of them are of absolute value 1. Right? Okay, so what can we do next? L S chi will be equal to 1 plus, as usual, integral from 1 to plus infinity d S chi of t divided by t to the s. This is basically Argus summation, right? So this is equal to 1 plus S chi of t over t to the s from 1 to plus infinity minus, s integral from 1 to plus infinity S chi of t divided by t to the s plus 1 dt, right? And what is the value of this?
Well, at infinity, you get something bounded divided by t, divided by infinity to the power s. So at infinity, you get 0. And at 1, you get 1. So this cancels out, and you are left with this integral, right? And this integral
At
is
1 we have what? 1.
1, because s chi of 1 is equal to 1.
Mm-hmm.
So this integral is absolutely convergent and even uniformly for sigma greater than epsilon, for any epsilon greater than 0.
So in any half plane to the right of your half plane, you get absolute and uniform convergence. So you have a holomorphic function. Okay. What can we do next? Well, we have an Euler product. If we have an Euler product, we can do something with primes. So let us take logarithm of L as chi. This will be sum over all p, logarithm of 1 minus chi of p over p to the s to the power minus 1. And then you should expand this into the Taylor series. So you have sum over all p, chi of p divided by p to the s plus chi of p squared divided by p to the double s multiplied by 2 plus chi of p cubed divided by 3p to the triple s plus and so on, right? So this is the sum over all p and k, chi of p to the k divided by k p to ks.
Where did the logarithm go?
What? Did I miss the logarithm anywhere? No? Okay, so we have this series.
And what is the use of this series? Well, assume that sigma is strictly greater than 1. Then you have this part with primes. And you have squares, cubes, and so on, right? The contributions of squares, cubes, and so on is uniformly bounded, right? Contribution of everything which is not prime here is bounded by the sum 1 over 2p squared plus 1 over 3p cubed and so on. And this sum is convergent. Correct? Assume sigma greater than 1, then we have the following formula. Logarithm of L s chi is equal to sum of all primes chi of p divided by p to the s plus big O of 1. And this big O is independent of Q and of character. Right? Okay, so now let us write down certain linear combination. So remember, we want to detect P congruent to A modulo Q, right? So let us fix A and consider sum over all chi modulo Q, chi of A conjugated multiplied by logarithm of L s chi. So this is a finite sum of some logarithms of holomorphic functions. What do we get here? Well, once again, sigma is greater than 1. Then we get sum over all chi modulo Q chi of A conjugated multiplied by sum of all p, chi of p divided by p to the s, plus some error term, which is big O of 1 summed of all characters. So it is, for example, big O of phi of q, right? Now this sum, or all these sums, are absolutely convergent. So you can change the order of summation, and you get sum of all primes, p to the power minus s, and then you have sum of all chi modulo q, chi of p, chi of A conjugated, plus some error terms. And what is the value of this sum? Can anyone tell me, please?
The inner sum.
Yeah, the inner sum.
Something like 0.
So it is a lot like 0, but not everywhere, right? What I claim is that
Sum over all chi modulo q, chi of p, chi of A bar is equal to phi of q if p is congruent to A modulo q and 0 otherwise. Right? So your A is invertible. A is invertible. So there is an A star such that A star is congruent to 1 modulo q. Right? So chi of A star is equal to chi of A to the power minus 1. And since chi of A is a root of unity, this inverse is actually equal to chi of A bar. So we actually sum chi of P A star. And we know by our theorem that this is equal to phi of q if P A star is congruent to 1 and 0 otherwise, right? That's it. So what do we get here? Here we get phi of q multiplied by the sum of all p congruent to 1 modulo q, 1 over p to the s, plus big O of phi of q.
Еще раз. У нас получается, вот как мы к этому пришли? То есть мы, получается, вот эту сумму, которая сверху, мы ее заменили на такую.
Да, и эта сумма равна нулю, если p со звездочкой не единица, и φ от q, если единица. По теореме.
Да. Хорошо. И потом... все. Так, и потом мы... все понятно.
Ничего не произошло.
Все.
Ага.
Okay, so
So this is an important thing. So we reduced
reduced our problem in some sense to some question about Dirichlet L functions. Right?
So we proved that certain linear combination of Dirichlet L functions
Is actually connected to the sum we would like to prove is infinite.
Yes, so to prove theorem 1, it suffices to show that sum over all chi modulo q, chi of A bar log L S chi has no limit at S equals 1.
So you can send your S to 1 from the right, and if you prove that there is no right limit, then of course the set of all primes which are congruent to A modulo Q is infinite. Right? If it was finite, then you would get this.
Oh, yes, okay.
So you at least has no limit. Sorry, is unbounded. We will prove that this function actually goes to infinity when s goes to 1.
Okay, it has no limit, it was okay, wasn't it?
No, formally you have to prove then that this stuff has limit as goes to 1, right? It is more or less obvious, but okay, let's be a little bit more pedantic with our statements. Okay. Now, what can one do with such a problem? Well, let me give you a sketch of the proof of theorem 1. It will use certain important lemma which we prove later. So it is written with K, right? I forgot. Скетч пишется через К или через... Ага.
Через C.
I think it's with K, okay. So let's look at our characters more closely. So L S chi is holomorphic when chi is non-principal. This means that logarithm. Let me restate. This means that L S chi is asymptotic to some constant dependent on chi multiplied by s minus 1 to the power m chi, where m chi is order of 0 at what? At s equals 1. Correct? This is due to the fact that this function is holomorphic. We take a Taylor expansion and then we see the asymptotics.
What is big A of
What is what?
What is big A of
Some constant. I don't care what this constant is. The first term is the first non-zero term in your Taylor expansion.
Okay. On the other hand, if chi is equal to chi 0q, then what is the value of L function? Let us evaluate it. Then Ls chi is equal to the product of all primes 1 minus chi 0q of p divided by p to the s to the power minus 1. Yeah? And this character is equal to 1 if p does not divide q and 0 otherwise, right? So this is equal to the product of all primes not dividing q, 1 minus 1 over p to the s to the power minus 1. Yeah? So this is, of course, the same as an Euler product for the Riemann zeta function. But we have thrown out some factors here. So this is equal to zeta of s multiplied by the product over all p dividing q, 1 minus 1 over p to the s. Correct? And as s goes to 1, this is asymptotic to what? Well, this is asymptotic to 1 over s minus 1, right? And this is asymptotic to a constant. This constant can be evaluated. This will be phi of q over q multiplied by 1 over s minus 1. Okay? So at least one term in our sum of logarithms has a singularity at 1. So what we, let me formulate the lemma. I will not number this lemma because we will prove only the least crucial part of this lemma. Okay, so lemma will be as follows: if chi modulo q is non-principal, then LS chi has no zero at at s equals 1. So okay, from this lemma we deduce theorem 1. Let me show you how. Well, m chi is equal to 0 if chi is non-principal. So logarithm L s chi is bounded at s equals 1 and s goes to 1, right? From the right. But logarithm of ls chi 0q is unbounded. Which concludes the proof, because let us look at our sum. Here you have one obviously unbounded term, and all other terms are bounded. And that's it. So what we proved is we deduced the Dirichlet theorem on primes in arithmetic progressions from this important statement.
And how do we prove this?
How do we prove this? So let me prove this statement for all characters, but maybe one. Okay, so lemma partial proof of lemma. So what I say is that there is at most one character modulo q such that L1 chi is equal to 0. The proof is easy. Let us consider the following sum. Sum without without the weight, logarithm L s chi. One can easily see that this is the sum of all p to the k congruent to a modulo q. Congruent to 1 modulo q. You should take this sum where this previous sum when a is equal to 1. If you take this sum, you will get sum over all p to the k congruent to 1 modulo q. And then you get 1 over k p to the ks, right? This means that product over all chi, L s chi, has
Можете повторить, как мы получили этот приход?
Which one? This?
Да.
So you take the Euler product, then you expand it, and then, for example, for primes, you are done. For squares of primes, you will get the same term, but with p squared, and 2 in the denominator. So all the coefficients will be something like this, right? Also, I forgot, of course, phi of q. But still, you have this formula, right? So this means that the product of all chi, ls chi, has non-negative coefficients. The reason for this non-negativity is because this is actually equal to the Dedekind zeta function of the cyclotomic extension. But this is far beyond the scope of this course. But still, one should know this fact, because probably this is the reason why Dirichlet started to consider such products. Okay, so this product has non-negative coefficients because it is an exponent of Dirichlet series with non-negative coefficients. And its first coefficient is equal to 1, right? Obviously, because it is an exponent. Exponent starts with 1. So, okay. Now what we do? Well, what do we do now? Well, if ls chi1 is equal to L1 chi1 is equal to L1 chi2 and is equal to 0, then product over all chi ls chi has a 0 at s equals 1, because you have one simple pole and at least 2 simple zeros, right? So your product should have a 0. But Dirichlet series with non-negative coefficients cannot have a 0 at point s equals 1, right? If it is convergent.
Еще раз, у нас получается...
Давайте по-русски попробуем. Значит, еще раз. У нас есть два характера, для них 0.
Да.
Рассмотрим вот такое произведение, у него не отрицательные коэффициенты.
Проблема.
Да.
Все понятно.
Okay, so the main thing here is non-negativity of coefficients. This is a very general situation in the context of some analysis, some analytic number theory, is that to prove something non-trivial, you should establish some non-negativity of something. So if you have some good non-negativity, yeah?
В чем проблема? У нас же, получается, казалось бы, если у нас один характер зануляет вот это произведение, в чем проблема того, что у нас два?
Потому что есть полюс еще. Один характер сокращает полюс, а другой создает
все.
Has zero because we have one pole and at least 2 zeros. Okay, so at most one character modulo Q such that L1 chi is equal to 0, and this character is real in the following sense: chi is equal to chi bar. So all the values of chi are real. So your character only has 3 possible values: 1, 0, and -1. Such characters are also called quadratic characters because they are connected with arithmetical properties of quadratic extensions of the field of rational numbers. Okay. So what we proved is that it is sufficient to prove that L1 chi is not equal to 0 when chi is a real character. And this is a main difficulty in the theory of primes and arithmetic progressions, because there are lots of examples when real characters present the most difficulty to deal with. Okay, so I explained the general strategy of dealing with primes and arithmetic progressions. Let me also give a definition, which will be important next time when we are going to prove some functional equations. So let me give a definition. Definition 1. Suppose that Q1 divides Q, and chi1 is a character modulo Q1. We say that chi1 induces chi modulo Q if chi of n is equal to the following. It is equal to chi1 of n if n and q are coprime and 0 otherwise. So this, as far as I understand, corresponds to induced representations, right? So if you have a character modulo Q1 and you have Q which is divisible by Q1, then you can induce a unique character this way, right? The next definition will be that chi modulo Q is primitive if it is induced only by itself. So if it is not induced by anything else, then it is primitive. Okay, so what we can do next is first, let me give you an example of primitive and non-primitive character. For example, chi 0q is never primitive for q greater than 1. So principal character is not primitive. Principal character is not primitive because it is induced by a principal character modulo 1. So by the identical unity. And for example, chi 4 is primitive.
One is a character, it's just all ones.
Yeah, it's identical unity. So chi 4 is primitive because it only can be induced by some character modulo divisor of 4, and if it is not, if it is induced by something else, not itself, then it should come from character modulo 2 or modulo 1. The only character modulo 1 is all ones, and the only character modulo 2 is 1 for odds and 0 for evens, right? It does not induce chi 4. You can also check that, for example, character chi sub p, which is the Legendre symbol modulo P. Is also primitive. Yeah, and let us prove a simple formula. So if chi1 induces, let us say this is lemma 1. If chi1 induces chi, then L function of chi is equal to the following. It is a product over all P dividing Q and not dividing Q1, 1 minus chi1 of P over P to the S multiplied by LS chi1. Proof is rather straightforward because LS chi is equal to the product over all primes 1 minus chi of P over P to the S to the power minus 1. And this is equal to the product of all P dividing, not dividing, sorry, this is completely wrong. This should be.
Как они у нас связаны между собой?
So Q is divisible by Q1. If you have a larger number, you can induce a character modulo this number from a character modulo a smaller number.
А может быть, вы тогда неправильно считаете?
Тогда вообще не так, потому что у нас любой делитель Q1 будет делить.
Да. Все-таки я неправильно поменял, да. Okay, so what is this product? This product is the same as the product of all P not dividing Q, 1 minus chi1 of P over P to the S, to the power minus 1, which is the same as the product over all P dividing, not dividing Q1, 1 minus chi1 of P over P to the S, to the power minus 1, multiplied by this product, right? Let me denote it by P of S, multiplied by P of S. And this product is by definition the L function of our inducing character, right? So this is an obvious analytic reason to consider only primitive characters. Why do we consider only primitive characters? For example, because if your character is not primitive, then you get
What does P of S stand for?
this product. So the clear analytic reason to study only primitive characters is as follows. If chi is not primitive, then the Riemann hypothesis is false for LS chi. Right? Indeed, you have this factorization, and if you take sorry, this is not actually true, and induced by chi1 modulo q1 such that there is a prime dividing q, but not q1. So of course you should be a little bit more precise here. If you have some character modulo q1 and q1 has less prime factors than q, then you have a violation of Riemann hypothesis. This is because you can take p to the s to be equal to chi1 of p, then then L S chi will be equal to 0, right? So this is the reason to study only primitive characters. But during the next lecture, we are going to go more in depth on this on this problem. So what we are going to do, we are going to establish a Fourier expansion for Dirichlet character. So we will study it as a function on Z over QZ. And it turns out that when you have a primitive character, you can just write down your Fourier expansion without any like problem. You have an easy, obvious formula. And if it's not primitive, then you have something else.
Also, we will establish the functional equation of the corresponding L function in the case where your character is primitive. Because of course, if your character is not primitive, then you have some additional factors in your L functions, and these factors are too simple to have a nice functional equation, right? Because if you change S to 1 minus S, there is no obvious relation between two finite products. This means that you should study analytic properties in case of primitivity. So that's it for today.
From the previous time, because we solved only the first problem. And let me remind you Perron's formula. It says that let f of s be a Dirichlet series for our sequence A. And
Sorry, can I find the problem set from the previous?
it is.
Okay.
Uh-huh. And also we know that if real part, if S is real and tends to 1, then such sum is before sigma minus 1 to the power minus alpha.
Значит, какая у нас задача?
It's Perron's formula. I remind you because we will use it in each program. And modulo AN is less than big A of n. When we have such formula, so the partial sum of our sequence, it is 1 over 2 pi and such integral. Here, b is bigger than 1, and you see that if t is large, then with remainder terms they are small. And our strategy generally is like that. We want to estimate such sum when we use Perron's formula, and then we want to compute this integral. And we compute this integral by shifting the contour to the left, because x to the power s is small when the real part of s is small. So we shift this contour to the left when we have sum of residues into this contour, and then we estimate integral over this this part of our contour. And when we optimize it, all parameters, I mean b, but b is usually 1 plus 1 over log x, it's a good choice in many situations, but not every time. And we optimize, we have these two terms, error term from estimation of integral over this contour, and when we optimize everything. And this is our strategy. Let us start with problem 2. It says that sum of mu of n over n to the power s is equal to 1 over zeta of s. We know this is this equality for if real part of s is bigger than 1, but we want to prove if real part of s is 1. It's problem 2. Okay, so we want to consider such partial sum, n is less than x, mu of n over n to the power s, and we want to say that if x is large, this is 1 over zeta of s plus something small. So we want to compute such sum. How we do this? Suggestions?
Нам очень хочется применить формулу Перрона.
Давайте применим. So our a n is mu of n over n to the power s. Then we have a n over n to the power, let it be not s, of course, because s in our problem is fixed, to the power, for example, w, okay? F of w. And what is f of w? And
We need to check some conditions on AN.
yes.
Ну это будет просто получается сумма n.
F of w is sum of what?
Mu of n over n w plus s.
Yes. This is if sigma is greater than 1, yes? And what's this? It can be represented in terms of zeta function. What's this?
Там mu от n
Mu of n?
степени омега плюс s.
Ага.
W.
Может, z от омега плюс от w плюс s?
Это тогда будет просто сумма 1 на n степень w плюс s. Это будет z плюс омега.
Сейчас, mu от n у нас, можете напомнить, как?
Функция мебиуса.
А?
Функция мебиуса.
Вот это мю от W. Нет.
Один двиг на света от плюс s.
Ага. 1 over zeta of s plus w.
Сейчас, почему так?
Because the definition of if you consider such Dirichlet series for this function, it's by definition, I mean, the definition of this function is that its coefficients in Dirichlet series. Okay, so we know that some, yes, here there is okay, and what will be our b here? You see, we don't have a pole. Now we don't have a pole at 1. If we sum the modulo of n, yes, sum of modulo of an. It will be 1 over n, yes. And so it has a pole at 0. It is because of sigma to the power -1, yes?
And it's big of 1.
No. If sigma tends to 0, this is not big of 1. So, so we can take B to be not 1 plus something, but 0 plus something. I mean, in our Peron's formula, it is written if we have a pole at 1, but of course there is nothing specific about 1. So the same holds if we have. So you can generalize it by change 1 by some more constant.
Еще раз. А можете напомнить у нас формула природы для каких сигма верна? Для сигма больших единиц?
На b больше единицы мы интегрируем, да? Мы берем b больше единицы.
Да.
До полюса. So here we will have sum of mu of n over n to the power s is equal to sum n is less or equal than x is equal to 1 over 2 pi integral b minus it to b plus it x to the power w, yes, we integrate over w. W zeta of s plus w, and what will be the remainder terms? They will be x to the power b t. I mean, here will be not b minus 1, but just b to the power alpha. Alpha in our case it is 1.
Why just B?
Huh?
Why just B?
Because here we assume that we have a pole at 1, but here we just shift everything to
То есть мы, получается, просто везде...
Ну, можно было в
честно
общем случае доказывать, что у вас особенность не в единице, а там где-то еще в точке А вещественной. И тогда вот то же самое получается. Проверьте, что plus b to the power b, I'm not sure, but
Here we have a pole at 0, right?
here, yes, we have pole at 0.
То есть мы все по вещественной части сдвигаем влево на 1, так?
Ну да.
Хорошо.
У нас вся теорема как бы сдвигается влево. Ну, можно было сразу в общем случае доказывать. And here we'll have a of x log x over t. And also we don't have such this x. No, it's x to the power 0. Okay, this is Peron's formula. And now what? What do we want to do? We want to shift our contour.
Сейчас еще раз можно просто с самого начала, что у нас произошло. То есть мы, получается, сначала записали f от w как 1 делить на z от сигма плюс w, от s плюс w.
Минус первый.
Ну, да, 1 делить на.
Да.
Вот. А потом вот что произошло?
Ну,
То есть можете вот
да, мы...
прояснить переход к...
Да, вот это b, мы вот этот
Такой записи.
интеграл, мы там, значит, мы нашу функцию представляли, как Перон доказывалось. У нас было n делить на n в степени s, когда это равно f от s, когда, собственно, ряд сходится. Поэтому это b, оно должно быть выбрано там, где у нас есть сходимость. Ну вот здесь сходимость будет при вещественной части больше нуля. Там, когда приближается, вот оно там будет так
Сейчас.
расходится. Ну, соответственно, мы то же самое могли делать просто не в окрестности единицы, а в окрестности нуля.
То есть, еще раз, мы, получается, просто все по вещественной части сдвинули на 1, во-первых.
Фактически,
Во-вторых,
да, так.
можете тогда пояснить вот переход, почему мы интеграл в таком виде записали?
Вот этот интеграл есть.
f от s, мы в таком виде записали все.
Ну, у нас теперь f от W просто.
Да, все. Сейчас, а куда у нас 2 беты x
Ну, 2
пропало?
беты тоже надо, 2 бета она никогда ни на что не влияет. Если вы b сверху
Хорошо, а x
боитесь.
куда у нас пропал?
А x вот потому что мы сдвинули все на единичку. Здесь там стоят на самом деле x в степени а, где вот этот конус.
Еще раз.
Ну, вот мы все сдвинули на единичку.
Да.
Ну, смотрите, если вот здесь вы сдвинете на единичку, например, у вас на x все разделится. Здесь, соответственно, единичку.
Сейчас еще раз. У нас куда x пропал из большого?
Ну, вот он,
Да.
откуда он появился? С
Да.
формулы пером. Ну, здесь он не появляется.
В формуле Перона, напомните, откуда появлялся у нас?
Ну, там остаточный член мы оценивали.
Так. Мы ее рассматривали в окрестности единицы.
Да.
И поэтому мы как раз-таки от x можем избавиться.
Ну, мы там x делить на n из степени s на s. Ну, что-то такое.
Мгм.
Ну, вот он x как бы в первой степени, в окрестности единички были. А теперь
У нас потому что s у нас все,
Да.
у нас сигма единица, все.
S.
Все понятно.
Okay, if you are not sure that this works, I should suggest you to look in some books. Peron's formula, it's famous formula. So just look at in a general case when this holds not for sigma in origin of in neighborhood of 1, but it diverges in some other point. So in our case we will have such expression, and let us take b 1 over log x, yes, so this will be what? B co of x over t multiplied by by x. There will be no x, yes, because b is 1 over log x, and this will be constant. It will be 1 log x over t. And here we will have what is a? What is a? It's 1. Okay, so these two terms are equal of log x over t. Okay? If we choose b, such a...
двухгруппность. Это что? Это же константа.
Ну, константа, да. Вот получается логарифм константы. Okay, now we shift contour. Who can do this?
Did we define a of and somehow or we just...
A of x?
Yeah.
Yes, it is 1 because
Okay.
these coefficients are bound. Okay, maybe I think someone should suggest what we should do.
Maybe just pure complex analysis, like...
Yes, we want to shift our contour. On previous lecture, we proved some zero-free regions that there are no zeros and some bounds. Let us the classical region is sigma is greater than 1 minus 1 over log t. Here s is sigma plus t. This is value percent zero-free region. And in this region, we didn't prove any Also, of course, we need upper bounds for 1 over zeta, yes? If we shift to a region, we need some upper bounds. We didn't prove any bounds, but actually you can prove that in this region, zeta of s to the power minus 1 is because of, I think, logarithm. Yes, but so okay. Let's use this, but also you can use simply a result that we proved that if sigma is greater than 1 minus 1 over logarithm to the power, I think 9, and where 1 over t to the first is because of logarithm t to the power 7. Yes, the proof was simpler. To prove this, you need some indeed complex analysis. You can shift to this, but the result will be the same. I mean, it will be 1 over zeta of s plus small of 1. But let's use this more nice contour. Okay.
Как у нас S и T связаны, я извиняюсь?
А? S это сильно плюс
Все, понял.
Т это.
Да, это я пропустил очень просто.
Okay, maybe you can do because it was not on the previous lecture.
Does this even make sense?
Ага.
Well, I need some time on it.
Okay.
So that I know what I'm doing with this.
You just need to shift the contour. What's
У нас получается тогда сигма будет больше, чем минус 1 делить на лог в 9, например. Сейчас еще раз мы...
Давайте вот этот используйте. Говорю,
Ладно,
чтобы
хорошо.
Там логарифм на что-нибудь будет степень.
Ладно.
Ага.
То есть получается у нас же он через 0 должен будет пройти,
У
нет?
нас
Ну, 0 внутри будет.
this is 0.
Ну, соответственно, контур давайте по минус 1 делить на лог t
Ага.
проведем.
А,
Нет, там получается...
We have a small problem that we also shifted by s. Yes, and s is not just 1, it's 1 plus. But I think s is fixed, so of course we can write the same result. But here of course there is some constant, small constant. Sorry. So the same will hold with some c. If we make it more smaller. Okay, so we shifted to what? It will be, here will be minus some constant over logarithm. Yes? Okay, and what's the integral over, so we have integral over this part, and now it is integral over all this contour minus integral over these three parts. And what's the integral over such contour?
It's the residue. The residue.
Yeah, what's the residue? We have, I think we have residue at 0.
1 divided by zeta of s.
No. We have poles, for example, if this is 0, yes? But that's why we shifted to the 0 free region. So we have only one pole at w is equal to 0.
0, yeah.
And then what's
I think it's 1 divided by zeta of s.
Yes. And if s is 1, this is 0. But when we don't have any residue, so that's fine. So this is equal to 1 over zeta of s plus what? Now we need to estimate our integral over this three parts. Let us estimate it over first.
Сейчас извиняюсь, а у нас еще раз вот 1 делить на z от s.
Ну, это вычет в нуле. Вывод ставим равно нулю.
Да, все, понял.
А здесь как раз 1 делить на 2π. Okay, what's how to estimate such integral? It's integral from
C divided by t.
minus c over log t up to b and what? How to estimate it? It's
Below it's plus I something.
Плюс и t, разве не должно быть?
Plus IT.
Я понял. Ну, я думал, сдвинуть все, чтобы вещественно все. Окей.
Сразу все
Let me write that. That integral over 1 of this expression, of module of this expression, is less than integral from minus c over t to v of what? Let us. Okay, what it will be? 1 over w, what it is? How to estimate?
We're trying to estimate this.
Yes, we want to estimate the integral of module, for example. Okay? Of module. Over this short line. What is 1 over omega of the absolute value?
One over absolute value.
How to estimate? Here. You see, this is big T.
Something like
1 over T. Yes? Okay?
Сейчас, почему это валидная оценка?
No,
it's a lower one. Okay, yeah.
it's upper bound. Here is multiplied by some constant. By 2. Ну, потому что оно порядка 1,19.
У нас Т большой достаточно.
Т большой, да.
Да, все понятно.
Большой, там вот это. Ага. Okay, what about zeta of s plus omega to the power minus 1? It's because of log t. Yes? And if we have such, here it will be because of logarithm to the power 7. And what is, and finally we have x to the power w. It will be x to the power sigma d sigma. Okay? And this is less than what? I think.
Т делить на Т.
Uh-huh.
Мы выносим константу.
And here what? Let us just write, that's it. And 1 here. Because x to the power sigma, it's always, in our situation, it's because 1, and we integrate it over short.
Сейчас у нас же сигма В окрестности нуля.
Ну да, да. Мы интегрируем.
Если у нас сигма...
Сигма
у нас
в степени b это e. Поэтому, ну, то есть это ограничено, и мы интегрируем по короткому отрезку единицы. Поэтому, ну,
Сейчас нет, там вопрос в другом. У нас, смотрите, у нас же получается сигма, она в окрестности нуля, причем, насколько я понимаю, она просто произвольное число из окрестности нуля. Ну, как относительно произвольное.
ну, в смысле, мы интегрируем. Спасибо.
Ладно. Еще раз, почему там единица получается? Потому что у нас...
Потому что вот это всегда не превосходит число e. Отрезок
понятно.
короткий. Okay. And the same for integral over this short line. And what about integral over this? How to estimate?
When the third part is estimated the same way.
Yes, yes, of course. They are conjugate. So what x to the power w? What how to estimate it? It will be the absolute value will be exactly what?
We can take 1 over c when
It will be x to the power minus c divided by logarithm. You see, if we shift to such to such region, here will be yes 9. But of course it's still small better than 1 over logarithm to negative 1.
Сейчас, еще раз, как мы получили это счастье? У нас...
Ну это к степени другого по модулю. When we have...
Сейчас, а почему нам W и Z?
Ничего такого. When we have also zeta, how to estimate zeta, again, it will be logarithm t. And how to estimate 1 over w, and we integrate over such line. Okay, here it will be. Okay, let us estimate like an integral from. Let us estimate integral over this. So from 0 up to t of what? It will be how to estimate?
IT.
Okay, let us change variable.
We estimate the part where one word.
I think we can estimate it integral from 0 to 1. And from 0 to 1, it is bigger than c over log t, yes?
Сейчас,
To the power minus 1.
сейчас log t, сейчас. Так, логарифм t большого или t малого?
Здесь t большой, здесь я интегрирую.
То есть мы константы интегрируем.
Да. Ну, потому что у нас 1 на W, оно по модулю самое большое вот в этой точке. Ну и от 0 до единицы. And then plus, and now if here it will be approximated just by 1 over t. So it will be plus integral from 1 up to t, 1 over t. And so it is less than x minus c log t to the power 2. And already we see that we can make it all these terms to be a small o of 1, and we solve our problem. But let us choose t to optimize their term. How to do it? So we have let's assume that t is less than x, yes? Then we have two terms. Big O of x c log t t square plus big O of log x over t.
Что со вторым сделать вообще непонятно, потому что асимптотика-то по x, правильно?
And now we choose t to optimize these two terms. Что? Мы t большой выбрали, у нас сколько?
Все равно же при фиксированном t логарифм надо стремиться к бесконечности в любом случае.
Да, ну t растет вместе с x, мы сейчас выберем. T мы можем выбирать. X у нас фиксирован, мы выбираем t в этом рассуждении.
То есть у нас получается вот эта вот вся сумма получилась вот суммой вот этих двух кошек.
Да.
Прекрасно.
How to optimize? Just let us choose t in such way that these two terms are approximately equal. So that x to the power minus 1 over log t is approximately 1 over t. Can we do that? How can we do it? Let us take logarithms. What does this mean? It means that logarithm x over logarithm t is logarithm t. Yes?
Сейчас, зачем мы именно так берем?
Ну, чтобы примерно они были равны.
Сейчас. Почему там минус 1 делить на лог, а не минус c?
Ну, если c будет чуть-чуть другой выбор, ну, на самом деле то же самое даст. So again, as on the lecture, when we
Должен быть.
что?
Кто примерно рядом?
Ну вот эти, мы хотим, чтобы их сумма была маленькой. Ну, оптимизируем по t, чтобы их сумма была маленькой. Ну, как надо оптимизировать? Чтобы примерно они были равны. Логарифмы, они ни на что не влияют, они маленькие. Вот примерно это равно этому. Но я говорю, что c можно... Да, c вот это.
Нет, ну, там же, в принципе, предполагает, что какая-то неизвестная константа.
Да-да-да, и здесь c, ну вот мы их примерно это все делаем, конечно. Потом посмотрим, просто они совпадут.
Сейчас сделали, что производит? Сейчас, секунду. У нас вот переход можете пояснить между этими двумя строчками? То есть, кажется, мы с одной стороны взяли производ...
Ну, логарифм взял. Здесь e в степени минус
А, все, там у нас минусы сократились, все, понятно.
So, logarithm, good choice is logarithm t square is equal to logarithm x. And when what is this? If logarithm t square is logarithm x. So what is, it will be big O of x to the power minus c over square root of logarithm x. Yes? So this will be if logarithm x is logarithm t square, then this will give us this is exponent of minus c logarithm x over log t. So it will be exponent of minus c square root of logarithm x. Okay? Do you agree? And I mean, these powers of logarithm, they do not matter because here we can change with c, make it smaller, and then this will so this logarithm will disappear. Is this clear? Because logarithm is exponent of double logarithm, and double logarithm is smaller than square root of logarithm. And here what it will be 1 over t. It's again 1 exponent of minus square root of logarithm x. Yes, by logarithm x, and of course this is smaller than this. I mean, you could choose it better, so this c constant is equal in each case, but it will be just the same constant, some number constant c here, small constant.
Формулу Перрона, что ограничение на вот это большое, ну, на второе большое, асимптотическое не зависит от t.
Да, более того, мы вот даже здесь пишем 2 в степени b, где-то не пишут, а где-то пишут, чтобы даже и от b не зависело. Там абсолютно константа. Оно, наверное, зависит вот от O большом в этом сигма минус 1 в степени минус альфа. Наверное, зависит, но это для фиксированной функции. Okay. Are there any questions about this problem? So we proved that sum n plus 1x of n to the power s is 1 over zeta of s plus the O of exponent of minus c square root of logarithm x. And of course this tends to 0. So let us solve the next problem. Okay, this next problem is
Можно упирать на основной экран.
а?
Можно теперь
Да, да, да,
на
да.
экран. Спасибо.
Oh, next problem. So now we want to compute such sum n from less than common x lambda of n over n to the power s. And we have here two cases. S is 1 and s is not equal to 1. And we want to compute it if real part of s is 1. Okay, I think now someone can do this. Please.
We can use Perron's formula.
Yes, yes, yes. Please, some.
Простите, я встретился с эфиром.
Okay, but that's okay because we just started to solve problem 3. We want to estimate such sum.
Ну, получается, надо использовать формулу Перрона. Тогда полагаем, что АН это у нас будет, ну, как раз вот это еще нужно? Нам нужно f от s. Тоже здесь будет f от w.
Можно писать это? Значит, все-таки S тут.
Нет, нет. Потому что у нас S здесь фиксирована
Это-
задача.
да.
Нам надо тогда здесь менять.
Так, это будет, получается, лямбда
Да, на S степени S плюс.
m степени s плюс. Так. Ну, теперь
А что это за вопрос?
хороший вопрос.
У нас была такая функция лямбда на S степени S плюс. Мы через
Это
неё-
штрих минус это свет на z.
Да,
На
да,
z.
это минус логарифмическое производное.
Так.
S плюс.
Так. Ну, получается сумма. Дальнейшее пробой x.
Ой-ой-ой, там дубль.
Ой, да. Ой. Тут есть наш. Я уже. Новый. Омега на. Ой, да. Так, и теперь вот с этим O большим.
Там везде x на единичку пишется, то есть x степени b так и останется.
Так, а тут у нас T.
Здесь будет b в степени просто b. b. Просто b. Хорошо, 2 степени b не будет писать. X.
Да, X.
Там будет
Ну,
what is a? A is logarithm. Yes, we
Да.
good function, but so it will be x logarithm square of x over t. And no x because we are
почему
here.
без X?
Ну мы в окрестности нуля.
Да. На T. Так. Ну, теперь надо опять этот контур рисовать.
А теперь тот же контур, да?
Да.
Как будет сигма больше. Сейчас давай.
Да, у нас сигма равна. Ну. Так. Получается, тоже будет как-то.
Значит,
Здесь будет T. Так, и здесь у нас
ну,
будет
быть маленькую
единица,
сцену, да?
а здесь будет, получается,
Ну,
минус.
единичка, здесь будет b, да?
Ой, b, да.
Эти маленькие.
Здесь будет минус c деленное.
Okay. Yes. Now we shift our contour to this value percent, zero free region, and also on the lecture we proved that this is because of square of logarithm. Actually, here you can make logarithm just, but again, logarithm will disappear because we can take C smooth in final form. Okay, and I think here we have the same estimates for such contours because everything is the same except for this bound, but it doesn't influence our final result. And just please find the residues.
Так, у нас получается будет.
Here we have two cases, S1 and S. The first case, S is not equal to 1.
S не равно.
Right?
Тогда у нас только будет W равно нулю.
Ну, еще,
И еще будет, когда у нас сама z
то есть,
равняется нулю.
то есть какой? Значит, в каких точках? W, можно W равно?
W равняется, ну, у нее нули в отрицательных целых. 1 минус. Вот. Так. В нуле это у нас будет, получается, единица, деленная на нуле. Единица.
Ой,
Ну вот как раз у нас.
я так перепутал просто.
От S.
Наверное, с минусом,
Да, и минус. V равняется единице минус S. Там у нас.
So now we find the residues at 0 is minus logarithmic derivative of z to s, and now at 1 minus s. Z logarithmic derivative minus it is I think it will be just 1 over 1
Ну, да, 1 делен на 1 делен минус S.
And also we have x here.
Да,
X to the power 1 minus x.
Ну, а по всем вот этим остальным там будет точно так же, как и мы в предыдущем задании делали.
Yes, yes. And so the final result, what will be the final result? Can you write it here? That such sum, lambda final. It is.
Сумму вот этих вычетов.
Plus we go. And it will be the same.
Ну, логарифм x делен.
Е степени минус c.
Нет, минус c.
Корень.
Но это в случае s равняется единице, s не равняется.
Yes, in this case s is not equal to 1.
Это просто используется для оценки прошлого упражнения.
Ну, то же самое, у нас ничего не поменялось.
Так, и s равняется единице.
Ага, да.
А,
It's more interesting.
Так, ну у нас точно так же будет v равняется нулю.
Yes, now we have only one pole at 0, but the residue is
Так.
I think here you should write your series at 0. So you have 1 over w, it's clear. X to the power w, it's what? What's the Taylor series at 0? Can you write, please? X to the power. It's a yes.
X он уже
Yes.
в окрестности нуля.
It's 1 plus.
Единица плюс v x понятно.
Log x. Yes. Log x. And etc. And now interesting. What is 1 over z of yes logarithmic derivative at 1 plus omega. What is series? Let's start with so we want to compute z of 1 plus omega, z of 1 plus omega. let us start with formula zeta. Here with minus, yes? With zeta of 1 plus omega, what is it? Zeta of 1 plus omega. It's 1 over omega plus what? Plus gamma, yes? Или Maclaurin constant. Или маскирование. Etc. And some other constant, yes? Plus gamma 1. Okay, now it will be enough. What's this series? Should be compute. Or maybe someone see it somehow immediately.
Да,
But this
получается,
series
мы можем,
compute logarithmic derivative.
мы, получается, можем просто продифференцировать и поделить на...
Yes, maybe you can take logarithm. Be clear.
Соответственно, конечно.
Oh, maybe just let's complete.
Так. Мы можем просто...
Ну, производный же,
Да. Получается, будет здесь минус единицы, наверное, квадрат, тут 0, гамма 1, и так далее. Тут минус. Так, а теперь как это делить?
Можно посмотреть на ряд.
Там,
Это минус зета штрих. Да.
это я просто
Start will hopefully something like minus 1 divided by omega starts plus plus gamma and then plus gamma.
Ну, тут будет не просто гамма. Плюс гамма, почему плюс гамма?
Давайте. В смысле, считаю 1 разделить на 1.
I forgot about the minus, but never mind.
Логика 2 разделить на 1 плюс гамма плюс минус. Ну, концерт как-то.
Так. Получается сейчас
Получается
минус 1 делено на омега плюс гамма плюс гамма 1. Сейчас.
только вот отсюда кинули, да?
Минус гамма
Ну, что
омега.
такое? То есть минус, здесь один минус, вот на это можно здесь второй, третий минус, но это минус гамма.
Да, я забыл про минус перед дробью, я извиняюсь. И перед 1 на омега тоже плюс будет.
Да. Ну, получается, вот здесь должен быть плюс.
Да.
Сейчас. Да. У нас
И нам нужно член при 1 делить на омегу.
Ага.
Значит, получается, нужно отсюда константы. То есть это будет... Я равно. Напишу. Это будет отсюда единица и минус гамма. Ну, здесь больше нигде констант не будет.
Ой, сейчас.
Вроде тоже. Нет, еще вот этот, вот x. Вот, x. И все. Плюс лог x на гамма.
Все.
Нет, мы берем вот отсюда единицу и минус гамма, а отсюда мы берем...
Вот и это.
Все, да. Плюс лог x. Да.
What's the final answer?
Получается...
Let's see.
Сумма.
Ну, пожалуйста.
Сумма та же самая. N меньше равно x. Минус гамма плюс x плюс большой. Оно будет то же самое, там, в степени x
And in particular, we see that logarithm x minus such expression tends to gamma. It's a problem.
Можно попросить, пожалуйста?
Okay, we have 20 more minutes. Let's solve number problem. In problem 4, we assume that such sum n over n to the power sigma converges if sigma is greater or equal to 1. So an is convergence sequence. And we asked to show that sum an is equal to a limit sigma tends to 1 and to the power sigma. And
Четвертый пункт.
да,
Там разве не 0 плюс? Пределник 0 плюс.
почему ноль?
Ну вот.
Если сигма...
там
так, сигма стремится к нулю.
Ничего не
Нет, ну у вас написано, что сигма стремится к 1 плюс.
Нужно написать. Спасибо. Что? Какой вопрос?
Сигма к нулю стремится.
Ну да. Ага. And this is... do you know Abel theorem, which says that if we have power series, and if we know that sum over an is so that an is convergent, then such limit tends to 1 minus sum an next to the power is less. Do you know this theorem?
Звучит очень знакомо.
Yes. For example, for example, 1 plus x is x minus x squared over 2 plus etc. And if you take x equal to 1, this will be 1 minus 1 over 2 plus etc. And this is convergent. And claim is that this is the limit of logarithm 1 plus x when x tends to 1, so this is logarithm 2. You know that this equality when your series is absolutely convergent, but it's on the boundary of circle of convergence. For example, in this theorem. So if this series converges, then this is equality. And here it's the same, but for Dirichlet series. And the proof is also the same. Do you?
Лично я вот того не знаю.
Очень знакомо, просто, возможно, она у нас бездоказательно появлялась в вопросе.
So it's Abel theorem. So we use Abel summation formula to prove it. Okay, so you can look at the proof of this, and then you will figure out the proof of this. But let us prove for Dirichlet series. The idea is to consider such sums as Sn. It will be partial sum of A. AM n is greater than n. And we may assume that such sum is 0 because we can change A1 in such a way that the sum will converge to 0. Yes?
Сейчас. Кажется, у нас это просто по теореме Абеля в чистом виде делается.
Ну здесь это же не ряд. В смысле,
У нас
это
эквивалент,
интерес.
потому что, да.
Здесь сигма.
Да, здесь он.
Чуть-чуть другой, но то же самое получается.
Мне кажется, это просто можно сказать, что мы ограничим тогда один делить на n в
Ну,
степени.
n в степени сигмы, x в степени n, это не очень понимаю.
Ну ладно, да.
I want to say that we can change A1 in such a way that so that such sum is 0. Let it be S is 0. Do you agree?
Yeah, because we can subtract the sum.
Yes, we just change A1. And now we want to prove that this tends to 0. And let us write our sum an over n to the power sigma in terms of Sn. So this will be sum of what? Sn minus Sn minus 1 over n to the power sigma. And now we can write it like a sum over Sn. Sn of n to the power minus sigma minus n plus 1 to the power minus sigma. Okay, and now we know that Sn tends to 0. Yes? So we divide this sum into two parts. We can sum it over n less than some big n. Sn n to the power minus sigma minus n plus 1 to the power minus sigma. Yes. And we see that if sigma tends to 0, this sum tends to 0 also. Yes. Do you agree? Because this will be 1 minus 1.
Для конечного количества очевидно, почему.
And now plus, and now we estimate we have these terms are all positive, yes? And Sn is bounded by maximum of n bigger than n modulo of Sn, yes? and how to estimate such sum? N bigger than big N, n to the power minus sigma minus n plus 1 to the power minus sigma. This is telescopic sum, yes, and so it's less or equal than n to the power minus sigma. Yes. So here it's n to the power minus sigma. Okay, and now we see that we can choose large n. When sigma tends to 0, we have bound for our sums with bounds. Okay. So in some neighborhood, they are bounded by 2 max of n bigger than n s n if sigma is less than epsilon, for some epsilon, and this tends to 0. Okay. And the proof of Abel theorem is the same, but it's just the same. But in other direction, it's of course it's not true. I mean, if you know that there is limit, so this series can be not convergent. Now, next exercise. We want to show. It's a part of it's for B. Show that logarithm zeta of s equals 2 to lambda of n less log n. So this is the Dirichlet series for logarithm zeta function that it holds for sigma equal to 1. Yes. Why it holds? Please use this Abel's theorem.
In this case, an is lambda n divided by logarithm n is
Lambda n divided by, I think if s is 1 plus it, we want 1 plus it logarithm n. I think in such way, yes, to reduce to our theorem. Yes. And when if this is convergent, then we have equality, because logarithm of zeta it is some. So we just use our theorem. Okay. But now we want to prove that this is convergent. Why this is convergent? Because we proved in the previous exercise that lambda of n to the power s, that this is I think x to the power 1 minus s, 1 minus s plus some constants, yes? And plus, we want to write minus derivative of z that is plus 1. And you see this is not a constant because I mean if we change x, it's not a constant, but it's x to the power to some imaginary power. So this oscillates, yes, it's exponent of 1 minus s, it's it minus it log x. Yes, it oscillates, but it's all of s is bounded. It's big O of 1. So, I mean, this is not divergent. It oscillates, but if we divide it by logarithm m, it becomes divergent by, for example, by Dirichlet criterion. Or just integrate by points. Okay, you will see that it is divergent. Okay, problem, and it's how we would solve problem 2, because for problem 1 we know that such yes, that mu of n over mu of n, such sums are small o of x, small o of x. Yes, it's from problem 1, and now we, for problem 2, we can use these others. We know that the series diverges and so converges, and so it should converge to 1 over z of s. Okay, we have 13 minutes. And he.
У нас вроде половина заканчивается. Ну, во
We
сколько
have 3
начали?
minutes.
Мы во сколько начали?
Да, в 10. Да.
10, ладно.
Okay, let me just say what about next exercises. Maybe you can think about them at home if you want. For some functions, we need bounds good bounds for zeta. For example, if we have such sequence, 2 to the power number of prime divisors. It's what will be Dirichlet series? It will be, I think, zeta square of s over zeta of 2s, something like that. And now we use, for example, we want to use Perron's formula. Yes, it's not only way to compute such partial sums. But for example, we want to use Perron's formula, so we need to shift our contour. But to where we can shift this contour? We know that zeta of 2s to power minus 1, it is it's
W это у нас количество простых делителей или...
простых различных. I want to say that we can shift this contour to this up to up to a half plus epsilon. This will because there will be no poles, right? And if we shift it further, there will be some zeros. So poles of 1. But when we need some bounds for zeta at this line, so we need some bounds for zeta at the crucial state. Yes. That's why these exercises are about some bounds for zeta function. And I have 1 minute. And how to do bounds for zeta? For if sigma is greater than 1, we know that it is we know the bound. Yes. Yes. Big O of logarithm t, and if greater 1 plus epsilon, it's just big O of 1. And then we can prove some bounds for if for real part less than 0 by functional equation. We just need that zeta of s is some function multiplied by zeta of 1 minus s, and we want to estimate such function. And this function is simple. It contains gamma function, and for gamma function we have Stirling formula, so we just finite work. And when we will have such formula, zeta of s is less than t to the power 1 over 2 minus sigma logarithm t in this region. And what about crucial strips? Here we can do it in different ways, but I think very good is this way that just let me present you what is written. For zeta function, let us, if we look at zeta function on such line, we will usually have some bound. Zeta of s is less than t to some power. Yes.
Извините, нам вот в верхней строчке что там получается, как читать правильно?
Что?
d в степени
1/2 минус сигма.
1/2 минус сигма умножить на логарифм.
Это вот здесь, да? То есть вот далеко это будут плохие оценки. Да. Вот on this line we have some bound t to the power a, and let us take infimum of a. Yes. For each sigma, and f of sigma will be such function. Okay? Is it a clear definition of such function? It's 7b. Yes. And the claim is, so we know this function, if greater than 1 it's 0, if less than 1 it will be, think like 1 over 2 minus sigma. What it will be like that. And what about here? And the claim is that this function is convex. We can prove it by some complex analysis. And the solution is written there. You please look at it. And so here at least we will have such. And for example, here we see that 1 over 2 plus it is less than t to the power 1 over 4 plus epsilon. So this is not really well. Okay, thank you.
Есть вопрос. Вот в самом начале там 5а, где гамма-функция оценивается в полосе. Написано, что вы видите из формулы Стирлинга. Это странно звучит, учитывая, что формула Стирлинга, она же вроде только на вещественном луче.
Нет, сейчас скажу. Стирлинг's formula is true in such region.
А мы остановили уже запись, да?
Ну, почему я отвечу на это еще плохо? Yes, the question is where Stirling formula holds. Yes, in such region.
Для любого угла.
Ага.
Сейчас, а как? То есть у нас получается для любого. То есть по факту везде, кроме левой половины вещественной оси.
Ну да, потому что там полюс угол.
А это можно как-то вывести из того, что формула Стирлинга верна на правом луче? Автоматически, через свойства там функции мероморфных.
Ну, это просто там как делается? По частям это интегрируется тоже. Ну, у нас есть произведение, где произведение, да? Значит, логарифм возьмем, и мы хотим логарифм оценить сумму. Ну и по частям там нужно, ну, не просто там, если это какой-то требует Да, получается. Так, а я не понял, я остановил трансляцию или нет?
Там оно... Давайте сейчас.
Она красная, значит идет.
Значит, еще идет.
Хорошо.